My name is Corbin Probasco. Today I'll be demonstrating my drone detection device. This device was intended to be an early warning system for potential dangerous drones, whether that be out in the mountains or in a city. This device functions with a very lightweight and small 32-bit microprocessor. It has very low power consumption and it has very cheap parts. This whole thing was constructed with under $200. It has cheap tuned antennas, individual radio controllers for each frequency, all of which were sourced for around $10 to $20. Now that caused some problems that I'll get into in a second, but for now this demonstration is demonstrating the 5.8 gigahertz frequency and the 2.4 gigahertz frequency. Those frequencies are common for, on the 5.8 gigahertz, FPV drones here in the US, and on the 2.4 gigahertz frequency, commercial drones like DJI, Mavic series, and other clones of the DJI drones. In order to demonstrate, I'm going to be simulating a spike in radio frequency output as if a drone was passing by. I don't have an FPV drone that I can test the 5.8 gigahertz frequency, and I don't have any drones that operate on the 2.4 gigahertz frequency for testing purposes. Later videos will come where I will test those frequencies with actual drones, but for this test on this version of the product, I'm going to be doing simulated spikes in frequency, and I'll explain how I do that. But first, I'm going to demonstrate how the device is operated. Now, it can operate on a portable battery. For this test, I'm going to be powering it with my laptop, and for debugging purposes as well. So the tone that you heard when it started, it confirms the configuration and initialization of these chips that I'm using. For the 5.8 gigahertz frequency, I have a simple logarithmic detector. Basically, it just sniffs that frequency and responds with how powerful the frequencies are on that band. Converts it into a voltage signal and displays it on this small screen over a serial port. As you can see, this cable is shielded. It's got copper shielding over it, as does the case that this whole thing is housed in. These devices are very sensitive to interference, and so to sort of help with that and help isolate the frequencies I want to be detecting, I made a Faraday cage for the chips and also the screen display cable. Now, in order to simulate a drone flying by causing a spike on the 5.8 gigahertz frequency, I'm going to calibrate the device to 0 input and then use the noise from the Wi-Fi router as my detection threshold. So in order to do that, I'm going to leave the logarithmic detector disconnected, signaling 0 input. Now I'm going to hit this button, which recalibrates the noise floor. The way that my software works is it gathers 100 samples on that frequency range, and then it averages out the noise, and then sets a threshold which can be tuned in sensitivity. Right now my threshold is fairly sensitive, which I think is where it would need to be in application. Every time you push this button, it recalibrates that noise floor. So let's say you're using it in the city and then you move out into the mountains, you would want to recalibrate the noise floor because there's going to be less interference in the mountains than the city. So right now I'm recalibrating. You can hear the tone that plays, signals that it has been recalibrated. Now I'm going to connect the logarithmic detector, which is going to cause a spike in about 1.3 voltage of input, which is massive. It's set up to detect as small as 0.2 or 0.1 increase in power on that band. Now when I plug this in, the alarm is going to signal that the 5.8 gigahertz frequency has detected a spike. That one tone that plays signals a spike. Now I'm going to move this closer so you can see the output on the screen. I don't know if this is going to be visible with the frame rate on the camera. So the 5.8 gigahertz frequency is labeled on top. DT stands for detection, and then it shows the voltage level. Now, If I had a drone to test with, I would then recalibrate to the noise floor of the surrounding area, which is about 1.3 volts. So I'll do that right now. Calibrating, signals that it's calibrated. And now the floor is about 1.8 voltage on the input right now, which is a signal strength of 5.8 gigahertz. That's coming from all of the routers in the surrounding complex. These routers transmit at a relatively low power in relation to what an FPV drone would be. FPV drones have pretty high power transmissions so that they can get through buildings, concrete, etc. And this device will work a lot better in the mountains when the noise floor is lower. The higher the noise floor is, the less accurate this device is and the more false positives you're going to receive. Now, I'm going to cut to when I have this configured to test 2.4 gigahertz. Now, as you can see, I have swapped out some of the antennas on this device. The reason for this is I found the cheapest Chinese clones of real devices that I could possibly find. The one that I'm working with on this 2.4 gigahertz frequency is so obscure I could not find a data sheet. So rather than spend months trying to trial and error figure out the parameters for this chip, I'm going to switch to 3 chips that I know well, which will be copies of this one here on the left that I've already shown you working. Now, for the sake of time, I'm going to demonstrate one more frequency with this chip. When this device is finished, all 4 of these frequencies will work in the same fashion, and that is the 915 megahertz frequency, the 433 megahertz frequency, 5.8 gigahertz frequency, and 2.4 gigahertz frequency. All these frequencies are common for drone use. The 433 and 915 are more common outside of the US. It's initialized to the 0 voltage noise floor. Now I'm going to be using the Wi-Fi once again to test this 2.4 gigahertz frequency input. The alarm should fire, signaling that the 2.4 frequency is detecting a spike. Yep, there it is. And so on the 2.4 gigahertz frequency, we're getting about 1.2 volts of input. That concludes this test of the device. There will be more in the future. Like I said, I'm waiting on 3 more chips to make all of these frequencies function simultaneously. Now I'm going to show you the modularity of the device, how it will work. This black cable would be the power source. This screen could be located on a backpack strap, maybe on a wrist. The casing has loops, if you can see here, for a strap. This could be strapped onto a backpack, a chest plate, anything that is used to carry gear. And then, once it's strapped on, the standard 4 frequencies that are the most common for use in drones can be attached. But when I get those other 3 chips that I have on the way, when I have them fully implemented, you could, in theory, attach any 4 frequencies that you want to detect onto this, like so. And these are all universal fittings. They can be swapped around, they can be changed, and this is a very versatile device. The waterproofing is not 100%, so that's something that I'm going to improve as well. But this concludes my first demonstration of the first version of this prototype. Now I figured I'd give a close-up of the circuitry involved here. So here's my screen. As you can see, it's updating. I'm going to reset the code and recalibrate. Alright, we've recalibrated to the noise floor of the apartment building. And these are the 2 frequencies that are hooked up currently. So as you can see, these chips that I've gotten from Amazon and all these other off-brand websites, they are extremely delicate. The soldering of this chip in particular was extremely difficult, and I suspect that the heat generated in the soldering process may have fried this one. Now this one, on the other hand, was actually pretty solid. I got lucky with this one. You can't see it right now because it's shielded, as it's very sensitive. You can see that shield connects to ground here just to isolate that frequency. Now I'm going to take 4 of these, or 3 of these, and attach them to each of these inputs. This will be a somewhat simpler device than I had originally intended, but my next version is going to actually decode the frequencies and pick out drone specific controls and commands, which would make it... I wanted to mention a few more technical details about the drone detector that I built. The protocols that I'm using for serial communication with the screen are I2C, and I'm using the SPI serial interface for the Chinese clone of the CC2500 RF controller. Now that's the chip that I'm having issues with, that I'm going to be replacing with a logarithmic detector, which the way that the logarithmic detector works is it just converts signal strength into a voltage. It's not that straightforward, but by using an analog to digital converter in the 32-bit processor that I'm using, the STM32, I can take the output, it's an analog output from the logarithmic detector, and I can convert it to a digital signal and operate based on the strength of that signal.